Hello everyone. This presentation is about the Wookey project and the result we got during our research. First, who we are. I'm David Berard. I'm a security researcher at Synactive. I do reverse engineering, vulnerability research, exploit development. I have done this research with Jeremy, which is also in our reverse engineering team. Synactive is an offensive security company based in France, and we are about 70 people and we are hiring. We have done this research because of the CESTI challenge. And this challenge is organized every 2 years by the French National Cybersecurity Agency. Synactive is a laboratory accredited by the agency to do software evaluation. So we have to do this challenge. Until this year, ANSI organized 2 different challenges, one for the hardware labs and one for the software labs. So Synactive is a software lab, so we only participated to software challenge until this year. And this year, ANSI chose to organize a unique challenge on a unique product, which is Wookey. The main objective is to evaluate the ability of software labs to do hardware sync and vice versa. Wookey is an open source and open hardware project developed by the agency. You can find all the source code, all the schematics on their GitHub. Basically, it's a USB mass storage device that stores your data encrypted on an SD card. And to be able to access to your data, you have to do 2 authentication with a touch screen that is on the device. First, the user has to enter a PET pin to authenticate the smart card. The Wookey will display a PET name. This name has to be checked by the user, and if the name is correct, then the user can trust the smart card. And a second authentication, which is called user pin, is used to decrypt data. Wookey uses multiple smart cards for multiple functionality. One for normal operation to get access to the data, one to enter in DFU mode, and one to sign firmware. A particularity of Wookey is to have a unique firmware per device, and the firmware contains encrypted secrets. Wookey is based on the STM32F4 MCU. It has a GTAG on debug boards, and it's disabled by STM32 protection on a production board. The memory protection unit is used to implement a multitask operating system, and several interfaces are used. The display is connected to the device with an SPI connection. The smart card communicates with the Wookey through 7816 bus, which is a serial bus. The user PC can be connected to the device with USB, and a low speed and the high speed port are on the board. A serial port can be used to get Wookey logs, and there are 2 buttons, one to enter in DFU mode and one to enter in reset the board. For the software, all the software components are developed by the agency. The bootloader initializes the hardware, performs security checks, and load the operating system. It's written in C code. The microkernel, which is called Ewok, is coded in ADA. It implements syscall for hardware usages, IPC communications, and the task scheduling. Developer chose ADA to build a safer and more secure kernel. Driver and task are written in C code and run in a non-privileged mode. The kernel used the memory protection unit to implement task isolation, and the syscalls are handled in ADA, and some permissions are applied at the build time on the task, and the syscall checks this permission at every call. The challenge was organized in different steps. First, the laboratories have to write a full test plan for the hardware and the software parts. Then the agency has selected some tests in our test plan. For Synactive, we have 2 software tests and 2 hardware tests selected. In software, the analysis of the kernel syscalls with fuzzing and source code review techniques, and the fuzzing of the library used to communicate with the smart card. And in hardware, we have to do the review of the secure channel establishment with the smart card and the power glitch attack against the STM32 RDP protection that is used to disable the G tag on the production boards. After all these tests, we wrote an assessment report and sent it to the agency. So let's start with the syscall test. We implemented a very basic fuzzer in a user learn task. ANSI gives us a debug board. So on this board, we are able to build and load a custom firmware, so we can add our task on it. So how the fuzzer works, it takes a random syscall number and do a call with selected arguments. Arguments are chosen in the list of random value, limit value, valid pointer to random data, etc. And the PC is connected to the serial port and waits to collect crashes. When a crash occurs, the Wookey reboots, and then the fuzzing task is re-executed, so the fuzzer continues to do testing. So many crashes were quickly found. We had to analyze them. The fuzzer found a way to write 0 at a controlled address in a privileged mode. So we used this vulnerability to write a privilege escalation exploit. It's relatively trivial to exploit. The register responsible to enable or disable the memory protection unit is memory mapped, so we can write on it. And write a 0 in this register means that the memory protection unit is disabled. So after writing a 0, our task can write everywhere in the memory, including the kernel code and data. So we use this to modify the kernel structure, the kernel task structure, to make our task in a privileged mode. We also do syscall code review, and we found that reading ADA code is not so easy for people not used to it to do it. We found small bugs, and we missed some bugs that the fuzzer has found. To conclude on syscall, basically ADA protects you from basic security bugs but for a kernel, user space addresses have to be correctly checked. So second software test is the test of the smart card communication library with fuzzing technique. So this library, it's C code, and it's easy to modify the library to make it standalone. So we were able to run this library on the PC and make the library pass smart card messages. So we built the library with libfuzzer and the address sanitizer and ran the test for a few days. We got a good coverage of the library code, but we didn't find any bugs on this library, and you will see later that analyzing this library was a good plan for hardware tests. So the first hardware test we did was the analysis of the secure channel establishment. So this channel is established between the Wookey and the smart card to exchange sensitive data. The objective of this test is to see if the Wookey respects its documentation. We have used a logic analyzer to capture frames that come from the smart card and the frames the Wookey sends to the smart card. And our logic analyzer have already a decoder for this protocol, so we just modify it to export data in PCAP format. So we were able to load the PCAP in Wireshark, and on Wireshark we wrote a custom dissector to analyze Wookey specific frames. So basically you can convert this, the result of the logic analyzer, to this, which is much more easy to understand. So with this result, we were able to check that the Wookey implement correctly the secure channel. So the next big part is the fault injection tests. We see that the Wookey use STM32 protection to disable GTAG. This protection is called RDP. STM32 has option bytes stored in memory, and the RDP is one of these bytes. The RDP protection can have 3 different states. First, RDP0 is the state where all debug features are enabled, including GTAG. So in this mode, which is the default mode when you receive the MCU, you can debug the code running on it, read the RAM and the flash memory. In RDP2 state, all the debug features are disabled, so there is no GTAG, no way to read memory. And RDP1, in RDP1, the flash memory is not readable, and the flash memory is where Wookey stored encrypted secrets. So you cannot access to the encrypted secret, and all the data in the flash memory are already on the GitHub, except the secret that is unique to the device. And when you switch to RDP2 states, you cannot downgrade to any other states. There is many public research on doing fault attack on this protection on the same MCU family. The idea is to inject a fault when the boot ROM reads the option byte. So the fault can be injected with power glitch, electromagnetics, or laser. Since the RDP2 is encoded in a flash memory with the value 0xCC, a single bit flip in the value can downgrade the protection to RDP1 state. So he used the RDP2 states on the production board, which means there is no debug possible. In source code review, we see that the developers are aware of these attacks, so they implement mitigation inside the bootloader. If the bootloader, for example, detects a wrong RDP value, then the flash memory is erased. So even if the attack success, you cannot read encrypted secrets. The objective of our test is to show that the Wookey cannot be downgraded to another RDP state. And to do that, we have to use cheap hardware for building our test bench. To perform the attack, we have to modify the board, and the ANSI requested to not modify the Wookey board. So we use STM32 discovery kit, and this board are cheap, so no problem if we break one or more. Discovery board schematics are public, so hardware modification are more easy. We can look at the schematic and see where we have to do the modifications. So we'll detail the modification we have to do. To inject a fault, we need to be able to inject a very short and precise power pulse. So to do that, we have to modify the hardware. First, we need to control the MCU power supply. On discovery boards, you can see there is a jumper in blue, which is used to measure power driven by the MCU. So we can just remove the jumper and connect our power supply on the pin. And to do the attack, we also need to control the reset pin, which is accessible on the discovery board. Short power cuts are not wanted on normal operation, and so there is many capacitors on the board to stabilize and filter the power supply. And to inject a power pulse, we need to remove them, so we just unsoldered them. Okay, so we have our target ready to be attacked. We need a test bench to perform the attack. We build our test bench with cheap components, an external power supply to provide power to the MCU, a multiplexer to switch from ground to power supply and generate the power pulse, GTAG probe to check if the attack success, and FPGA to control all the attacks. So the FPGA have to drive the multiplexer, forward the serial port to the PC, and drive the reset pin. So here is our test bench. You can see there is multiple oscilloscope probes. It's very important to check that all the signals are transferred correctly to the target. So how we inject a power pulse? First, our PC send to the FPGA the attack parameter, so the width and the delay. The FPGA reset the board and waits the delay. The multiplexer is then switched, so the MCU power supply is now connected to ground. Then the FPGA waits the width and switch the multiplexer. So at this moment, the MCU is reconnected to the power supply. And to finish, the PC tries to connect on the target with GTAG to check if we have downgraded RDP protection. For the attack, we need to know the good parameters. To find them, we tried all the value in the specific range. If we try to pulse, to do a power pulse larger than 15 FPGA cycle, then the MCU crash always. So we choose the range 1 to 15. And for the delay, you can see on the oscilloscope that it's easy to spot when the bootloader starts, because it initializes the serial port and you can see it on the line. So we targeted all the time from the reset to the bootloader initialization. So we set up our test bench to test all the combination of width and delay parameter. On this phase took days because there is a lot of combination. And you can see in yellow here the voltage, and you can spot the glitch which is injected. On the next, you can see that we cover a large time frame. So on each try, we collect data. We try GTAG connection and save the GTAG connection logs, and also we save bootloader logs on the serial port to analyze later. After trying all parameter combination multiple times, we didn't success to get a GTAG connection. At multiple times, the Wookey bootloader has detected our attack and erased flash data, so protection are relatively resistant. We looked at the serial port logs. We have many crashes, panic, value inconsistencies, jump in state machine, etc. And we try to replay the parameter that produce this log, and we have a good reproduction rate, so it's interesting. And we see in the source code that the bootloader is the only component where mitigation are applied, so we looked at other components. The smart card communication library has already been analyzed during software testing, so we know a bit about how it works. It's an interesting entry point because it's parse message from the smart card before the user authentication. So we did a rapid source code review to find places where a glitch can create a software vulnerability. We find this kind of code inside the smart card message parser. The answer to reset is the first message sent by the smart card. Here you can see that a copy is done from the frame to a stack buffer, and a 4-bit size is took from the message to do the copy. So if a glitch affects the size, then we can have a stack overflow. So here we can see that the size is masked with a single instruction. So if a glitch makes the instruction to be not executed, the unmasked size will be used in the next instruction, and the stack buffer overflow can occur. But Wookey should have stack cookies, so even if we trigger the stack overflow, normally we only do a crash. But stack cookie are present in the binary. Stack cookie code is present in the binary, but it's not used. A typo in the build chain prevents the compiler to build stack cookie protected code. So there is no stack cookie at all in all the Wookey code at the moment of the evaluation. So we have done a proof of concept of this Stack Overflow. Since our target is the discovery board, there is no smart card communication on this board. So we write similar code in the user-learn task. The similar code produces the same assembly code than the smart card library. And to synchronize our fault injection, we had some logs on the UART to be able to see when we have to inject the fault. So here you can see the test and message on the UART, and we have to inject a fault just before this message. Here in blue you can see the voltage and the glitch injection. As for the RDP downgrade test, we have to check many values of parameters. So we define ranges to target, and we run the test for few hours. And like for the other test, we collect all serial messages, and we see that the Stack Overflow occurred because the program counter has been controlled. So the attack works, but there is a low reproduction rate. On the oscilloscope, we saw that the serial messages are not stable in the temporal position. This is due to all the things the board do before executing the target code, like doing hardware things, multiple context switch, etc. And we ran the attack during few days, and we saw that we can improve parameters. For example, on the graph here, we can see that 7 FPGA cycle seems to be the optimal value for width. To conclude on this part, we only did the attack on the discovery board. On the real hardware, we have to implement the smart card protocol in our fault injection setup. On Wookey, we think that we can improve reproduction rate by synchronizing the injection with the smart card frames. So we did a proof of concept to show that we can gain code execution on the Wookey with a single fault. The code execution can be chained with the syscall vulnerability to gain privileged code execution. And we see two scenarios that can be done with these vulnerabilities. First, we can dump the encrypted secrets from the firmware and clone the Wookey. And second, we can modify the firmware directly with the privileged code execution. So to conclude the presentation, Wookey uses a smart card for cryptographic operations. So if we gain code execution before user authentication, we cannot access to decrypted data. And all the vulnerability we found has been patched since our tests. So except for complex attack scenario, your data are still safe. If you have any question, don't hesitate to ask them.
Thanks, David, for the talk. So we have some questions that have been asked in the IRC channel. The first one is your glitch on the VDD, and it works, but did you try on the CLK?
No, we only tried to do it in power fault injection because there is some public research on that method, and we know that it can work.
Okay, so second question, you use your own FPGA MUX setup. Why did you not take the within make solution like Chip Whisperer or something else?
We already had the FPGA on the working setup at Synactive, and we already use this setup on other projects. So we already have a working setup to use for the Wookey challenge.
Okay. There was another question that I'm not sure is for this talk or the previous one. Did you open source your PCAPE modification or not?
Not yet, but I think it can be possible to open source it.
Okay. And my question is, you say you spend 7 days for some part, and all of those all the process to finish a challenge, because it seems to be very long activity.
The major part of the time is wait for result. For example, the glitch on the RDP protection took about 5 or 7 days to cover all the possibilities.
Okay, but is this a limitation of the material you need to try to reset, or why you need so much time?
Because each try took time. You have to reset the board, try a parameter, wait a little to be able to check if the JTAG is enabled or not. So each try took more or less a second. So it took a lot of time to reproduce all the parameters we have to cover.
Okay, and you stop as soon you find one, or you need to research all of them?
For the RDP protection, since we were unable to bypass it, we had to cover all the parameter ranges.
Okay. Impressive work. In any case, congratulations. You were talking about the ADA programming languages at the beginning, and you say this is not easy. And what are the advantages of this, according to you, against the C language? What was the difficulty you face in this challenge with this language? And do you think it has been done by purpose by the designer of the challenge or not?
So the ADA language was chosen by the developer to improve code security. Unlike C, it's a strongly typed language. So, for example, you cannot have basic memory bugs. And it's difficult to read for beginner because, for example, you don't know when exactly where there is a dereference, for example. So you have to learn to understand the code.
Okay. And maybe a last question from my side, if there is not other question on the chat or on the IRC. How much does it cost to mount all this attack in terms of material? Because you say you have many probes, many extra material to realize it? What is the total budget of this attack?
Except for the oscilloscope and the PC that drives the attack, the FPGA costs 200 euros, I think, and other material cost so maybe for a few euros, so the total is 3,000 euros.
Okay.
And there is a cheaper setup that exists, and you can buy it for similar performances.
Okay. And you didn't break the Wookey key when you were doing this experiment, because it's a risk, no, to crash the board. And if you crash the board, you need to redo everything, or you can reuse some previous analysis.
If you crash which board? Sorry.
If you crash the card, I don't know, by a problem or something like that, you need to redo all the processes or not?
No, you have just to reprogram the FPGA and redo the attack.
Okay. So thank you very much.